Today, we're going to add to the list of derivatives that we know. Right now, all we got is the derivative of a power function, which proved to be very useful. We could use some algebra to write a function as a sum of power functions, and then we got to use our nice shortcut, multiply by the exponent, subtract 1 from the exponent. Then we learned about the chain rule. That's when instead of x to the n, we had some function raised to the n power. The derivative of a composition of functions says we take the derivative of the outside with respect to the inside, then we multiply by the derivative of the inside with respect to x. And that gets us our overall derivative with respect to x. But there's more to life than polynomials and radical functions. There's more to life than power functions. So let's start adding to the list of base functions that we can work with. We want to build a bunch of base functions and then add up some optional extras like the chain rule and stuff like that. Ways to take those base functions and combine them. So first new category is going to be exponential and logarithmic functions. I like to group things with their inverses. So I look at exponential functions, and we're going to look at the inverse of the exponential function, the logarithmic function. So we're going to reverse the roles of the base and the exponent. With our power function, the variable is the base and the exponent is a constant. We're just going to switch those around, make the base a constant and the variable the exponent. So we don't want to do xa to the x minus 1 because that's for power functions. X is the variable. So we move things around. A is the base is constant. The exponent is the variable. We're not going to derive this with the definition of the derivative. We're just going to write down the end results. Remember, in shortcuts, we're playing the role of the engineer, not the role of the philosopher. We don't care why it works, we just care that it works. So the derivative of a to the x is a to the x times the natural log of a. The derivative of a to the x is a to the x times the natural log of a. So the derivative of 5 to the x is 5 to the x times the natural log of 5. Interesting thing about exponential functions is we can always adjust the base. If we have a function that says 1.08 to the x over 4 because something is increasing by 8% every 4 units, we can write that as an e to the constant times x function. So notice that the derivative of a to the x is a to the x times the natural log of a. That means if the base is e, the base of the natural logarithm, we get the following. The derivative of e to the x is e to the x. This is going to be our favorite. The derivative of e to the x is e to the x. We don't have to write natural log of e because natural log of e is 1. Natural log of e is asking the question, e to what power is e? And the answer, 1. So here is an important thing to remember. This one is the big deal. So the derivative of e to the x is e to the x. When we have a function a to the x, I can write it with a base of e, but I will have to adjust the exponent. I'll have to have a constant be multiplied by the x. So what we really want is to apply the chain rule to the derivative of e to the x. So what we actually really want is the derivative of e to some constant times x, e to the kx. And we have a constant times x. So k is a constant. We use c all over the place for other things, like the speed of light, and there's a plus c, but it's going to be a capital C. So I didn't want to use the c here, so we'll use the mortal constant. So the derivative of e to the kx, and we're just going to use the chain rule. The derivative of e to the something is e to that thing times the derivative of that thing. So the derivative of e to the kx is e to the kx times the derivative of kx, which is just k. And this is going to be one of our most useful derivatives. Every time I start using k as a constant, all I can think of is that it is the mortal constant, and then the song plays in my head. Mortal constant. And I'm handing out the test. Test your might. You turn it in. Fatality. In Mortal Kombat, that would be a fatality. I like pull out a paper and I hold it up and it has a big old F on it. And the student just goes, and the head explodes. So the derivative of e to the kx is k e to the kx. If we have something fancier up there, so let's have the derivative of e to the 5x. So for example, if we want the derivative, let's do something decreasing. E to the 0.1x is going to be e to the 0.1x times 0.1. That's all. Super simple. Barely an inconvenience. This is just something that you have to remember. Coming at this with the definition requires that we do a little bit more work with some limits, but we can calculate limits just by plugging in numbers that are close to 0. So it's not that much trouble. I just think right now it's more important for you to remember that the derivative of e to the kx is k e to the kx. Let's add to our list. The inverse of an exponential function is a logarithmic function. And just like with our exponential function, we're going to be most concerned with the natural log. So we're going to list that one next. The derivative of the natural log of x is 1 over x. This is for us right now, just something that you get to remember forever, starting today. The derivative of natural log of x is 1 over x. This one is really cool because we take the derivative of this transcendental function, natural log, and it comes out with a rational function. That's crazy. In the e to the kx, we had k e to the kx. It kept its form. That's also crazy. But it makes sense if we think about what exponential functions are used to model. You know, the exponential functions for exponential growth and decay. And exponential growth happens when the rates of change of the population or the function is proportional to the size of the population itself or function itself. So that one is as expected for our understanding of exponential functions. This is kind of crazy. The derivative of natural log of x is 1 over x. You go from the transcendental function, take the derivative, and land on a rational function. The chain rule is always in effect. So if I have if I want the derivative of the natural log of x squared minus 3x minus 4, I'll have the derivative of natural log of something is 1 over that thing. Times the derivative of that thing. Always remember your chain rule.
Right. Last time we
I haven't done product rule and closure rule yet. I saved those for later. We can get enough mileage on chain rule. Plus, we got to learn these kind of core derivatives that we're going to use for building blocks. So don't forget your chain rule. Every time we do the chain rule, I think of the David Bowie song. Chain rule. The derivative of e to the kx is k e to the kx. The derivative of natural log of x is 1 over x. The derivative of natural log of a thing is 1 over that thing times the derivative of the thing. How's everybody okay? Yeah. If we had something more complicated in our exponential function, we would do the same thing. So if, for example, I wanted the derivative with respect to x of e to the x squared minus 3x minus 4. The derivative of e to the something is e to that thing. So the derivative of e to the something is e to that thing times the derivative of that thing. E is constant. So chain rule is always in effect, because that sometimes the derivative of the inside is just 1. Type these two derivatives into your memory and click save. All you have to do is remember it forever. We're just adding to the list of stuff we know. Any questions before we go on to the next category? That previous section had some examples and lots of talking. It has two things for you to remember going forward. We need some trigonometric functions. Derivative of sine of x is cosine of x. Yeah. You start with the sines and cosines, you're just going to go around in circles. Not circles, there's four. It's 4 steps. Squares. Turn them sideways. Diamonds. It's not back and forth, it's a square. What happens is the derivative of cosine x is minus sine x. -1 times sine x. We should keep in mind our chain rule that is always in effect and look at the slightly modified kx version. The derivative of sine of kx is cosine of kx times the derivative of kx, which is just k. We like to write constant factors in front of our trig functions rather than afterwards, so we're sure that the k is not part of the cosine. It's k times cosine kx. The parentheses make that clear, but sometimes we get a bit lazy and don't write parentheses. The derivative of cosine of kx is minus sine kx times the derivative of kx, which is k. And if we go back around, the derivative of negative sine x, that will take us to negative cosine x. Derivative of negative cosine x will get us back to sine x. The chain rule is always in effect. Constant times x is a nice, easy one to remember. It helps remind you of the chain rule. So rather than just remember the derivative of sine x is cosine x, the derivative of sine of kx is k cosine kx. But the chain rule is always in play. So as an example, if I want the derivative of the cosine of, let's say, x squared minus 3x minus 4, the derivative of the cosine of a thing is minus sine of that thing times the derivative of that thing. The derivative in this case has more than one term, so I'm going to write 2x minus 3 in parentheses. Two more derivatives to just remember. Type them into your memory and click save. Oh no, there's more trig functions just out of space on this page. The ones to know are sine, cosine, tangent, and secant. We usually go have, like in trig class, for the full set, we get the cosecant and cotangent. We could address those here, but there's not really a lot that you can do with secants and cosecants and cotangents that you can't do with tangents and secants. So those are going to be the more important ones. But here are two trig functions that we should, derivatives of trig functions that we need to remember, starting now and going on until forever. Good question. How's everybody? Next, we're going to do tangent and secant. These are fun because they do weird stuff. Sines and cosines, nice and simple. Tangents and secants do some weird stuff. The derivative of tangent x is secant squared x. That's weird. The power goes up by 1. Derivative of tangent is secant squared x.
Do you know why?
Yeah, that's just how the slopes work out. That was me dodging a question, by the way. You all should recognize what that looks like. Does that have an answer? Yes. I can't do a full matrix. So notice that we have just one power of tangent and it goes up to a secant squared. Remember that our notation, when we write secant squared x, we mean the secant of x squared. Now, that's terrible. That's not how we say it at all. We mean the square of the secant of x. So we mean this. We write the 2 by the secant, but we're like, oh, what that really means is we do the secant of x, and then we square the result. It's the square of the secant of x. We definitely don't want to read that one as secant x squared, because that would be the secant of the square of x. And this is not that. This is the square of the secant of x. Composition of functions is not commutative. So just remember that when we write secant squared, we mean the square of the secant of x. The order of operations is take the secant of x, then square the result. But that's an interesting thing that tangent does. The derivative of tangent goes to secant squared. The derivative of secant is secant x tangent x. So it also has 2. Usually when we're trying to remember these, we take off the of x part so that we can just remember the essential bits. We say the derivative of tangent is secant squared. The derivative of secant is secant tangent. That's a nice casual way to say it when we're just trying to remember stuff. But if you find yourself in a formal situation, you want to be like, oh, the derivative of tangent x is secant squared x. And if you want to be more formal, the derivative of secant of x is secant of x times tangent of x. Then if you want to be extraordinarily formal and pedantic, you'd be like, oh, are you sure that's what you mean? Because you didn't speak any parentheses. You're like, oh, fine. The derivative of secant of x is the product of the secant of x and the tangent of x. And then multiple cases. You want to say the product of before, so you don't think it's the secant of x tangent x. At which point you're like, oh, you knew what I meant. So 2 more to remember. These ones look kind of weird, especially secant. So for example, if we had the derivative of the secant of x squared minus 3x minus 4. The derivative of secant of a thing is secant of that thing times tangent of that thing. Derivative of secant of this stuff is secant times tangent times the derivative of the inside. No, we have not yet begun to get complicated. No, this is just one chain rule. Once we throw product rule and quotient rule in there, then we can get messy.
Starting to get complicated.
Yes. Here's the good news. Once we have our base derivatives, product rule, quotient rule, and chain rule, there is not a derivative, or there is not a function that I can throw together where you can't find the derivative, given time and proper motivation. It's all over for derivatives. Once you have those three rules, you don't even need all three. You just need product rule and chain rule. Once you have those two rules and all your base derivatives, it's all over for derivatives. You essentially have complete knowledge of derivatives. All we can do now is add more base derivatives. When we try to invert this process, when we try to go from the derivative to where it came from, that's a mess. In fact, there are functions that we can write down that aren't the derivative of something. It's really weird. You think a process that was so self-contained would have a self-contained inverse, but that is not the case.
I still have no idea what the anti-derivative.
Natural log of cosine, minus natural log of cosine. So, two more derivatives to remember. Derivative of tangent is secant squared. Derivative of secant is secant tangent. You can remember them that way. But remember, if you just write tangent, if you just write the tan without anything after it, you haven't written anything yet. You've said half of a sentence. The trig function on its own doesn't mean anything. So for example, this derivative of tangent x, this is not two things here. This is one thing, the tangent of x, it's one thing. Writing this derivative of tangent actually doesn't mean anything. This is not a separate piece. How's that, okay?
Yeah.
Those are the four trigonometric derivatives you need to know. Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared. The derivative of secant is secant tangent. Type those in your memory. Click save. Correct. The cool thing about derivatives is we can get away with just knowing two derivatives of inverse trig functions. We really should know three: inverse sine, inverse tangent, and inverse secant. But we start with these two. And then later on with integration, we pick up the third one. But these are the ones that you should learn right now. The derivative of inverse tangent. I'm going to write arctan. The derivative of arctangent, which is inverse tangent, is 1 over 1 plus x squared. another cool bridge between a transcendental function and a rational function. That's good. Question.
Thank you. That's the.
The other one that I want you to know right now, the derivative of arc sine is 1 over 1 minus x squared. This only seems like a lot to remember because it's a lot to remember. And you have to remember all of it, all the time, in perfect detail. So, all right, that is kind of a lot. Why do it all at once? You just put it all back to this one day where you wrote everything down. This one day where you can refer to this one page of notes for all your basic derivatives. You know what? We should have a complete set. So the other arc trig, inverse trig function that you'd want to have carrying around, arc cosine, we can just get away with arc sine stuff. This is another one that we'll want to know. Derivative of arc secant. This one doesn't come up as much, mainly because I forget to use it all that often. Until we start doing trigonometric substitution in Calc 2. So then we get to Calc 2 and I go, oh yeah, trigonometric substitution. Did I ever talk about the derivative of arc secant? And then I realize I haven't. So let's have a complete set. The derivative of arc secant of x. Now, if I tell you what the derivative of arc secant x is, for some reason, just having all these on one day will make you instantly remember them forever, and calculus becomes so much easier for the rest of your life. All I have to do is fill in the derivative of arc secant of x, but I have to do it right now. If I don't do this right now, then we're just going to have to go through calculus at the normal rate. You won't instantly understand calculus. So let's fill in the derivative of arc secant right now so that we can all collectively instantly understand calculus all the way through to the end and not have to do any more work. But I have to do it now. If I don't, then the spell fails and we have to go through calculus at the normal rate. So let's do that. Ready? The derivative of arc secant is, oh dang, look at the time. I guess this will just have to wait until tomorrow, or you can go and look it up today. But I think the spell has already failed. I should have called Dr. Strange in on this one. That's going to do it for today. I will see you all on tomorrow. Learn these derivatives, and we'll practice using them tomorrow with the chain rule. Everybody have a good day, and thanks for playing.